All right. Where were we? We now understand Newton's method and how to do it really, really quickly, especially with the use of our calculators. Let's take a look at this. Find both solutions correct to 6 decimal places. The natural log of x equals 1 over x minus 3. So you might think, hey, if we wanted to find solutions here, couldn't we just solve for x, like isolate x? Good luck with that. We're just algebraically, we're not going to be able to isolate x in this situation, but we can use Newton's method. Let me jump over to my paper. Find both solutions correct to 6 places. We're going to be able to get each solution to its 6 decimal place accuracy. Okay, how are we going to do that? The natural log of x equals 1 over x minus 3. We need to think of this equation as a function that we're trying to find the root of. What we can do is set one side to 0. I'm going to subtract this 1 over x minus 3 like so. So this will act as our f of x, and the x value that makes it equal 0 is obviously the root. Okay, let me write that again. And you know what, when I do, I'm going to think of 1 over x minus 3 as x minus 3 to the negative 1. So that when I take a derivative, a little bit easier, I've got 1 over x, and this will be plus x minus 3 to the negative 2. Then I'd multiply, chain rule, so I'd multiply by this derivative, but that's just 1, so I got it right there. Okay, looking good so far. But now notice in this problem, we're trying to find 2 different numbers, and they don't give us any starting points. So let's think. We need to choose x1s graphically. I have no idea where to begin looking at that function where it might equal 0. So I'm gonna hop on over to Desmos. Y equals natural log of x minus 1 over x minus 3. Interesting. Okay, so we see, yeah, there are 2 zeros, kind of a funky looking function, but there are 2 places where it crosses the x-axis. Now Desmos will, if you click on your function, it will highlight those points, and we could see where those zeros are to 3 decimal places, but we need, of course, better accuracy than that. We want 6 decimal places. And obviously we're going to use this new cool method. I'm going to begin with the greater of the 2 solutions. We'll come back to this one. Let me kind of hone in here. So we can see this 0, the closest integer is at 4. So what will end up being a good choice for x1 for this greater solution is to start with x1 equals 4. Let's talk about why that would be a good idea, besides just the fact that it's the closest integer. And let's even think about what to be aware of, like what would not be a good starting point. At 4, right, think about tangent lines. So let me come in a little closer. The tangent line here at 4, right, if we kind of imagine it sort of coming down, it hits and it sort of grazes by like that. Would the 0 of that tangent line be closer to the actual 0 than we were to begin with, right? So if we started at 4 and that tangent line's coming down, just sort of visualizing, would this 0 get us closer to the number? And if it does, it's probably a good choice. And I think that will happen with 4. That tangent line is going to come down somewhere around here, and we're going to end up closer than we were originally. Now kind of think about the next step. What would that tangent line do? Well, this value on the function would be down here somewhere. And now that tangent line's a little bit steeper even, so that's going to bring us real close. And the 0 of that next line is even better. And then we can kind of imagine even better, even better, even better. So 4 would be a good choice. What if we were to say pick, or consider picking 5? Now, why would you pick 5 versus 4? Okay, but this will show us what we should be on the lookout for. If we picked 5, the point's up here. That's a fairly shallow tangent line. Let's think about what would happen. This tangent line would lead us way back over this direction. So I'm not sure exactly where, right? But that tangent line's kind of shooting us back over here, somewhere between 2 and 3, probably. Well, did we get further away from the 0? Maybe, maybe not, but okay, what would happen next? We'd find the next point up here someplace, and then we would follow that tangent line, and that's definitely leading us further away from the 0 that we are trying to hone in on. So we'd be up here, we'd kind of go in, and it would probably end up leading us, all these other tangent lines would end up leading us closer to this other solution down here. So if we're trying to find this 0, we probably don't want to pick 5 to begin with. 3, there's actually an asymptote. What if we picked 3.5? Why not? There's no rule says you have to pick an integer number, although generally I'd recommend that. But if you went with 3.5, let's see, that tangent line's actually pretty steep, right? It's going to get you in pretty close here. And then that next one, probably if you started with 3.5, that's going to get you a little bit higher accuracy faster than starting with 4. They're both going to work. They're both going to zero in there, but I bet 3.5 will be more accurate a little bit faster. Okay. But the point of this is, kind of consider graphically what your tangent lines are doing. Now, so I think we'll take 4 to be x1 to get this guy. What about over here? Looks like the closest thing is 1. Will this be a good choice? Yeah, if we see that tangent line, it's coming down about right there is the 0. We do another one. Yep, that's going to lead us in real close to there. So, okay, so we'll take x1 to be 4 for this one, x1 to be 1 for this one. Even here, what, if you were to say pick 2, that tangent line would be leading you in closer. Nothing wrong with that in this case, although we might as well go with 1. Okay. Let's go back to it. We'll take x1 to equal 4 for the larger one. Let's see what happens. To get x2. I like to write this part out just because I'm going to be typing it into my calculator, right? So we begin with x1, subtract, and then it's the original function divided by the derivative. So we'll have the natural log of x1 minus 3 to the negative 1 over 1 over x1 plus x1 minus 3 to the negative 2. And we'll need parentheses there and there. Okay, let's see what happens. So I'm going to begin with 4, enter. And then wherever I see x1, let's put an answer. So answer minus parentheses, natural log answer, parentheses, minus parentheses, answer minus 3 to the negative 1. Parentheses, that's my numerator. All right, divided by parentheses 1 over answer plus parentheses Answer -3 parentheses to the -2. Finally, close parentheses. Oh man, hopefully that will do it. Let's see. Okay, yeah. It's a little bit less than 4. That's what I expected. It looks like this was all correct, and it's getting closer to that 0. So I'm going to record every decimal I see there. X2 equals 3.690964511. So far, so good. Let's do it again. Now, check this out. Like, remember, they didn't tell us, find X3 or find X4. They said, do this correct to 6 decimal places. What does that mean? Let's see. What happens if we do this again? All right, highlight there, hit enter again. Ooh, all right. So it got lower, and then it got a little bit bigger because it kind of went too far to the left. Now it's coming back to the right. Makes sense. It's what we saw graphically. 3.7507262187. Okay. It's getting a little bit more accurate. Let's do it again. What are we looking for? Aha, here we go. Notice when I did the 4th one, some of those decimal places repeated. Well, because it's becoming more accurate, every time it repeats, it's locking in those values. 3.7556711965. And I saw that 75 repeated. I'm going to keep doing this until 6 decimal places repeat from the previous one. And then I'll know that I've got this accurate to 6 decimal places. Okay, X5 is 3.755700865. And we got now 3 places to repeat. And that next one's real close. Oftentimes what you'll find is, here nothing repeated, then 2, then 3. Sometimes there'll be this leap, and all of a sudden you're done. And I think that's even what happens right now. 3.755700866. Look at that. All of these. Now we've got 1, 2, 3, 4. We've got 8 places repeated. And so we know one of these solutions is going to be at, if we just take the first 6, 3.75570 are the first 6 decimal places of that solution. Now you might think, hey, that last place, shouldn't we round it up because of the 8? You could. I wouldn't argue with you to round that to a 1. But just the nature of the question, it said get it correct to 6 decimal places. I'm almost thinking like these are the first 6 decimal places of that 0, even though that rounds that decimal place would be a 0. Okay, kind of side by side here. Let's take X1. We were going to take X1 equals 1. Okay. So I think, am I going to have to redo all this? No, you know what? I don't think I will. Here's what I'm going to do. I'm just going to type in 1, enter, and then scroll up right there. And I think we can just jump to it. So X2 happens to be exactly 0.6. Okay. Then again, I can kind of scroll up. And here we go. There's X3, 0.651165,622. We got the 6 to repeat. X4, 0.653. 057, 431. We got the 6.5. What's the next one? X5, 0.65, 3059, 729. Let's see. We got, 5 places to repeat. We're going to need one more. Both of these needing 6 rounds. 059. Oh, everything repeated there. Okay, then the other solution, 0.653059, and that's 6 decimal places. I'll leave it like that. We got it. Pretty cool. Okay. Again, kind of even in our work, we could tell if this was all playing out the way we wanted to, if we picked starting X values that worked, because every time we do another iteration, we can see that it's like honing in on one number, right? Both times it did that. If you pick something that's off, what will happen is these numbers, or if you're typing it in wrong, right? These numbers will just be like changing wildly. They'll get really big, really small, or just really, really big. They won't be, they'll be just hopping around all over the place, and they won't be zeroing in the way that our values of X zeroed in on both of these values. So be aware of that. Okay. We've got one more. One more example. Let's take a look at it. This is a cool one. Approximate the 6th root of 50 correct to 4 decimal places. What? That's not a solution. That's not a 0. Oh, check it out. Approximate the 6th root of 50 to 4 decimal places. We're going to think of the 6th root of 50 as being the solution to an equation. That is the solution to x to the 6th minus 50 equals 0. Right? Wouldn't it be if we were to solve for x here, we'd get the 6th root of 50. So if this is our function and we find the 0, we got the approximation we want. Okay. Pretty clever. What's the derivative? 6x to the 5th. Okay. What about a starting value? Well, we could graph x to the 6th minus 50, right? That's a possibility for us. How might they have done this in the old days? What's another possibility? Another way to do it, and there's nothing wrong with graphing here and approaching it that way, but just to kind of show you a little bit something different. Could we get x1 without a graph? Here's what we might do. Just guess integers and see what integer comes the closest. Okay, so you might think, well, let's see, 1 would not come very close to equaling 0, x equals 1. Maybe x equals 2. What is 2 to the 6th minus 50? Let's see, grab my calculator. 2 to the 6th minus 50 is 14. That's actually not all that far away from 0 considering. How about x equals 3? 3 to the 6th minus 50. Okay, that's 679. So we're not going to go with this. I think the closest we can get, right, at x equals 1, 1 to the 6 minus 50 is negative 49. So the closest thing we have is 14 coming from x equaling 2. This would not be a good choice. Let's start with x equals 2. I know we don't see the graph, so we can't like kind of see where those tangent lines are going, but we'll be able to tell really fast if it's working or not, just based on our answers to use in our iterative formula. Okay. So we'll take x1 equal to 2. What's x2 then? Well, it's x1 minus, we've got x1 to the 6 minus 50 over 6x1 to the 5th. We'll need parentheses, parentheses. Okay. What would that give us? Going over here, 2, enter. Now I'll go answer minus parentheses, answer to the 6th minus 50 divided by 6, answer to the 5th. Okay, it's a number pretty close to 2, a little bit less than 2, which makes sense based on what we found up here. 1.927083333. If we do it again, it should be a number still pretty close. Okay, I think we're onto it. X3, 1.919. 459616. We got the 9 to repeat. And if we keep going, x4, and now this time we just need to get it to 4 places, 919, 383111. We got the 919. I think one more and we'll have it. It's probably going to be that 3. Yep. 1.919383104. We got lots of places to repeat. So our answer 1.919. I'm going to go with the 3. You could round it to a 4. That is approximately the 6th root of 50. Pretty amazing, or at least it's accurate to within 4 decimal places. That's pretty nice. So we can find interesting approximations like that. We could solve, I mean, that previous example, we can solve any equation. Well, solve in the sense of we can get an approximation for the solution so long as we know how to take a derivative. We can do that. Pretty powerful. Okay. Hey, that's it for Newton's method and 4.8.